Hi, good morning. My name is Shinji Sato from Kochi University of Technology. And I'm very happy to introduce a keynote speech on tsunami disaster mitigation by two-level design. As you guessed from the title of this talk, my talk is based on our experience in 2011 Tohoku tsunami, which devastated the eastern coast of Japan 9 years ago. Firstly, I'd like to describe very quickly about the characteristics of the tsunami, which was a mega tsunami with return period of 1,000 years. Then, a new strategy of tsunami disaster mitigation based on two-level design will be described. Firstly, very quick review of the tsunami based on the article published in the Japan Academy. The Tohoku tsunami was generated in a very large source area extending from Japan Trench to the coast. This picture shows the initial tsunami profile proposed by Fuji et al., which is actually inversely conjectured profile from a number of tide gauges. Tsunami propagation was then simulated by the long wave theory. This picture shows a tsunami profile 6 minutes after the shaking. You can clearly confirm that the tsunami has a directionality such that it's enhanced for east-west, but the north-south propagation will be not significant. And in about half an hour, the tsunami hit the coast like Kamaishi and Onahama and affected a long stretch of coastline in the East Japan. The impact of tsunami was investigated by a good coordination of joint survey group. On this occasion, I'd like to appreciate many international collaborations in the joint survey. The survey results were immediately shared on the web and widely used in rescue and recovery activities. The tsunami watermark height was as large as 40 meters above sea level in Sanriku coast. The tsunami watermark heights in past tsunamis are plotted on the right. Please note that the tsunami height in Chilean tsunami is different from the others. If we compare the tsunami height and the size of affected area, definitely the 2011 Tohoku tsunami was the largest tsunami in the history. However, there is one exception, that is Jougan Tsunami in 869. The tsunami is documented in an old document only in a few lines. Therefore, the details are still unknown. However, geological record surveys in 1990s and numerical simulation study in 2008 revealed that the tsunami size was as large as the 2011 Tohoku tsunami. This means that such mega tsunami, like Jougan and 2011, will be developed once in 1,000 years. Going back to the 2011 tsunami, many seawalls were collapsed. Let me show you some pictures starting from the north. This picture shows Tony in Iwate Prefecture. And massive seawalls were collapsed. The seawall height is more than 10 meters. And the whole area behind the seawalls was flooded. This is Soma in Fukushima Prefecture. On this site, all seawalls with height about 6 meters were flushed away. This is Nakoso, the southernmost city of Fukushima Prefecture. And there, the parapet part of seawalls was collapsed. And in all these examples, seawalls appeared to be useless for large tsunamis. The last picture in Ibaraki Prefecture, Hokota, the tsunami height was about 1 meter larger than the seawall height. It's not clear from this picture, but the seawall was intact and the damage behind the seawalls appeared to be small. And these examples appear to indicate that the seawall will be effective for tsunami damage reduction in case the tsunami overflow depth is about 1 meter. Since seawall will be designed for water level below the top of the structure, it is natural that the seawalls will be collapsed for overflowing tsunamis. This video is a laboratory experiment showing a concrete riprap seawall flushed away by an overflowing tsunami. In contrast, as I explained earlier, seawalls appear to be effective in case the overflow depth is of the order of 1 meter. This picture shows a house in Nakoso protected behind a seawall with 6 meter height. Tsunami level there was 7 to 8 meter, and therefore overflow depth must be of the order of 1 meter. The coastal area close to the seawall was inundated. However, the damage of the houses was very small. The clear contrast in the damage level indicates both the effectiveness of the seawall and the limitation of the seawall. However, in the news media, the effectiveness of seawalls were not reported appropriately. Many people start to consider seawalls were useless. So this is so-called no more giant seawalls movement. The discussion was made from various aspects like high cost, inappropriate consideration for localities, rapid recovery, but the little attention to consensus building. Too high sea walls must be a burden to community restoration. And the effectiveness of sea walls is rarely described. Historically, the seawall height in Sanriku coast was determined on the basis of past tsunami height. This picture shows the along-shore distribution of tsunami height in Iwate Prefecture, together with the seawall height determined on the basis of these tsunami data. Seawall height that appears to be at the upper level of the tsunami height. However, it's not at the maximum. This means that sea walls are not enough to prevent the damage. We have to combine the evacuation plan in order to minimize the damage. Tsunami height data by 2011 Tohoku tsunami is red. They are mostly larger than the seawall height. Japanese government decided to introduce a two-level design to accommodate the mega tsunami. In order to describe that two-level design, I like to use a schematic diagram. As I mentioned, tsunami disaster mitigation in Japan has been composed of hard countermeasure plus soft countermeasures. This picture is a schematic diagram showing the tsunami damage on the negative axis and tsunami height on the horizontal axis. And tsunami damage will accelerating the increased with the tsunami height. Once we introduce the design tsunami level, then we can construct the sea walls of this height, and then the damage will be below this level, will be avoided like this. So this is how the hard countermeasure, which is a structure-based tangible countermeasure, achieve disaster prevention. The structure is designed for the design tsunami level so that it is not expected the structure will be effective for tsunami larger than the design level. Therefore, I put the damage level will be unchanged for the larger tsunami. However, tsunami heights are highly variable, as I showed for the case of Iwate, so that we have to combine the hard countermeasure with the soft countermeasure. Soft countermeasures such as early evacuation and the city planning is intangible countermeasure, and that will decrease the damage, so that this must be a disaster reduction rather than disaster prevention. So this is the idea of tsunami disaster mitigation even before 2011 Tohoku tsunami. However, before 2011 tsunami, no specific tsunami height had been proposed for the soft countermeasures, which resulted in inconsistent evacuation plan implemented from one place to another. And after 2011 Tohoku tsunami, the target tsunami for evacuation plan is introduced as the level 2 tsunami. The frequency of level 2 tsunami must be very small, like once in 1,000 years. 869 Jougan Tsunami, 2011 Tohoku Tsunami must be among level 2 tsunami. In contrast, the level 1 tsunami will be used for the design of structures. The frequency of level 1 tsunami will be once in 100 years, considering the lifetime of concrete structures and also the lifetime of human beings. Furthermore, structures are somewhat durable for tsunamis larger than the design level. In case we are successful in designing the behavior of seawalls against overflowing tsunamis, then the damage will be partially decreased by such structures. This is called as the structure with NEBARI. NEBARI is a Japanese word representing tenacity or toughness or resilience or beyond the design performance. Then the damage will be furthermore minimized. It's something like a small wrestler showing the last minute, never give up performance. Okay, seawalls with NEBARI are introduced in many places. This picture shows a seawall in Sendai reconstructed in 2014. Heavy concrete blocks were used on the backside. This is a sea and this is the land side, so the backside of the structure. And foundation of the seawall was reinforced to avoid the scour by the tsunami overflow. And going back to the seawall height in Iwate Prefecture, level 1 tsunami was determined on the basis of all tsunami height data, including 2011 Tohoku tsunami, together with numerical simulation. And they are represented by red triangles, which is in between 10 and 15 meter, and some are even smaller. And the data of 2011 Tohoku tsunami will be used as the level 2 tsunami, which is more than 20 meter. Okay, in this way, the Japanese government, in Japan, the two-level design concept is being achieved. And this is the summary of my talk. And once again, the level 1 tsunami will be used for protection, which is the frequency is once in 100 years. And level 2 tsunami will be used for evacuation, and the frequency will be once in 1,000 years. And structures with NEBARI must be investigated further, and we also pay attention to the how to avoid the overconfidence of seawalls. that must be investigated further. Okay, thank you very much for your kind attention.